Good morning. Can you hear me?
Yes, yes.
Okay. This morning's seminar is video. Okay, let's start.
Hello everyone, my name is Mitoko Kawa. I'm a faculty of the Life and Environmental Sciences in University of Tsukuba. I'm sorry that I cannot be here in person because I'm currently on a maternity leave, which means I have a baby in my home. So I'm recording the lecture as a video, and hopefully you can learn valuable things from my lecture. So the title of my lecture is Measurement of Food Quality. Before we begin this lecture, I would like to show you how you can post your questions to this lecture because I cannot be answering your questions directly in the classroom. I would first like you to get your smartphones or PCs if you are connected to the internet, and open your internet browser, which can be Google Chrome or Safari or Internet Explorer, whatever you are using. And please type in Slido, S-L-I-D-O. Oops. Cannot see my. Please go to Slido, S-L-I-D-O. You will find the first website here. Click it, and then on the page you will see a part where you can enter your event code, which is R244. So enter your event code and click join. Okay, when you click this, you will see several tabs. There's one tab to write your questions. You don't have to write your name. It can be anonymous. So write whatever you want. And you can write in Japanese or English. There's also another tab you will see where I have a question for you. It's a simple question of how much you would pay to buy an apple, because that's kind of part of this lecture. So we will see if everyone answers that question. We will see like how many people would pay how much for an apple, and that's what I also want to see. So please answer that question as well. And during the lecture, during the lunchtime, please post your questions. I will take time at the end of the lecture to answer it. I don't know how I will be doing that. Maybe I will go to the university. Maybe I will write it in text. But I will answer your questions at the end. So please post some questions there. Okay, so we would like to begin this lecture by asking this question: why should we even have to measure food quality? So I think there are two different goals or objectives for measuring food quality. One is to separate damaged or bad products from good ones. The other is to separate high quality products from normal ones. Okay, so two goals. Let's look at the first one. Why do we need to separate damaged products from good ones? Well, what would happen if we leave damaged products together with undamaged products? Okay, let's think about that. For the second point, why should we separate high quality products from normal ones? Well, because customers should be able to choose between high quality and high price or low quality and low price. And that's part of the question that I was asking you. So how much would you pay for an apple? Probably you as students don't have much money, right? So you don't have much money to pay for a very expensive apple, even if you know that it's very high quality. And so, but maybe if you begin work, you have a lot of you get a lot of salary, then you might say, okay, I will pay more to get a better apple. So consumers should have the choice to choose what they want. But even if we have the choice, what would happen if this quality that we are aiming for is unclear or subjective, which means even if you do pay a lot of money, you don't get the high quality that you want. That's a problem, right? So I would like to look into that problem here. Okay. So why should we measure quality? And I said that the first objective is to separate damaged products from good ones. So let's think of what would happen if we leave damaged products together with undamaged ones. So maybe you know the proverb, one rotten apple spoils the barrel. Barrel means the whole box. So this means that if you have a box of apples and you have one apple which is bad, it will spoil the whole box. This proverb means that we normally use this with like people. So if you have a classroom and there's one student who is bad, he or she will use his influence to make everyone bad. So it's not a very nice proverb. But to take this literally, this, as the word says, it's the same. It actually happens. So if you have a box of apples, and if let's say one apple has a pinhole, which is a small hole, and with apples or any other fruit, the skin is very important to protect the whole apple. So if there's a small hole in it, then through this hole, this apple is going to begin to rot, which means it begins to become bad. This rotten area grows, and as this area grows, this will be a place where all the bacteria from the outside will go inside the apple, and then the bacteria will increase. As the bacteria increases, because there's a lot of bacteria around or microorganisms around, this will influence other fruits. So even though it begins with a small hole, after 2-3 weeks, it's going to go get the whole box. So what we need to do, we need to find this one apple with a pinhole and get it out before it affects the whole box. Right? That's why we should separate damaged products from good ones. So the second objective is to separate high quality products from normal ones. You can see this is another apple example where it's in Japanese, but you'll see that the apple on the left, it's 68 yen for one apple, which is quite cheap, I think. The one on the left is 68 yen for one apple. The one on the right is 580 yen per apple. So that's almost 10 times, well, 9 times maybe. So you can see that there's a lot of difference in price. So we should think that this one on the right is maybe sweeter or more tastier than the one on the left, right? So let's imagine that you have a lot of money today and you pay 580 yen for an apple, and you go home, you eat it, and you find that it's rotten or it's not very sweet. You would be quite angry, right? So we need to have very clear or objective evaluation for this quality when we want to set the price for something. So we need to separate high quality products from normal ones. That's the second objective. Okay. So thinking about these objectives, I would like to first go through the content of the lecture today. First, I would like to think of what is monitoring. And I will talk to you that there's two types of monitoring methods. One is one-point measurement, and the other is multiple-point measurement. So what's this? Okay, then because I will talk about measuring with light today, basically, that's also what I do for my research. So I would like to go through some basics of measurement with light. So what is wavelength or energy? What kind of measuring methods are there with light? And a very, very important law when measuring with light, which is called the Lambert-Beer law. Okay. When you talk about light, you also need to talk about colors. That's a very important thing with light. So I would like to talk about how colors are expressed. And then finally, I would like to talk about some examples of how we can use light to monitor food or evaluate food. Okay, so this is the basic content for today's lecture. So first, what is monitoring? Monitoring means real-time observation and measurement. And even though we have a lot of machines in the factory, and we know that AI or is machine vision that's very hot today, even today, most of the work is done with the human eye. And you can imagine that standing up all day, looking at each, this is orange here, but looking at each orange, checking if it is good or not, that's very, very tiresome work. Okay, so it is long work. It's, simple labor, which means, there's no change every day. It's not so difficult maybe, but imagine you do it all day for many, many days. That's very tiring, right? So if we can introduce some machines in here, we can avoid long hour work and simple labor. It's also a problem with fruits, vegetables, is that they are harvested in a relatively short period, especially fruits. So if it's apples, it's autumn. If it's oranges, it's in the winter. And you get a lot of harvest in a very short time, which means there's a lot of work to do during that time. But then when that period ends, then there's no more work. So when you have people do that, that means that you have a lot of work for a lot of people in a short time. What do you do after that? Okay, so long hour work, simple labor, we can avoid that with machines. You can enable objective and stable evaluation, which means, you have a lot of people here. Do you know if this person will evaluate the same as the next person? You don't know about that. So you want all the evaluation to be the same and objective, right? You don't also, maybe a person is not feeling well one day, tired, sleepy. That kind of thing happens with humans. So with machines, you can enable objective and stable evaluation. There are things that you can also detect that are difficult to detect with the human eye. For example, metals. Maybe humans can't see metals if it's in the inside, something. So these things you can detect with machines. And also you can measure things that cannot be measured with the human eye. For example, sugar content. Sugar is white, or it doesn't have any color to the human eye, which means that we cannot look at it orange and see if it's white, if it's very good or not, if it's sweet or not. Okay, so with machines, we can use light that humans cannot see to measure things that humans cannot measure. That's also a good thing about machines. And I talked that there's two types of measurement, 1 point and multiple point. Okay, 1 point measurement is just, it means what it says. It means that you take one measurement point per sample, and you use that one value to describe the average quality of the sample, average. Okay, this is an example where they are measuring the sugar content of melons. What happens is that the melon is on a belt conveyor and it's on a cushion like this. There's a hole in the cushion, and there's a detector or machine sensor in this hole. You see the light, it is shining from right, the light right, and then this light goes through the melon and then into this detector, and there's only one sensor here, so you get the average sugar content of this melon. It's very simple. The good part is that you don't have to build a big machine for this. It's only 1 point, one measurement per sample. Multiple point means that they are lots of measuring points per measurement. And the easiest thing that you can see with that is imaging. So with imaging, you have lots of sensors to get an image, right? Because you have to measure every point of in an image. So every pixel, we say, and that has multiple or lots and lots of sensors. All the pixels in a camera they are all sensors. And so by using this multiple point measurement, or you can just imagine a camera, you can measure the distribution or position of components, not just the average, but you can see where is it sweet, or in this case, where is the wound or the spoiled part. Right? You can imagine that there is much more data than 1 point measurement. So you have data here, all this data. And so because of this lot of data, this machine can be expensive. So there's good things about multiple point measurement. There's also bad things about multiple point measurement. Okay, so those are the two types of monitoring methods, and I want you to remember that. Okay, now let's go on to the second part, the basics of measurement with light. Because today we will talk mainly about measurement with light. You may know a little bit about this, so if you know it, you can just listen. If you don't know much about it, please listen carefully because it's very important. I think if you're going to use light in the future for your research, even if you're not, this basics is very important. So you know that light is basically a wave. And so because it's a wave, there's many parameters that you need to know. So there's the wavelength, which is the length for one wave, like this, which goes up and down. Yeah, wavelength, which we normally write as lambda. And wave number is the opposite of wavelength, which means how many waves are there in 1 meter or 1 centimeter. Okay, so that's 1 divided by wavelength. Frequency is how many times do you get a wave in 1 second, for example. And you can calculate that by dividing the speed of light, c, by the wavelength. Okay, and the energy is the Planck constant h times the frequency. So if you put this frequency part, change it with c divided by lambda, you get this. Right? What to remember, the thing to remember here is that when you see, if you can see this equation, if you have a high frequency, you get high energy. If you have a short wavelength, you get high energy. Okay? So, short wavelength means large frequency, which means large energy. Okay? Short wave.
So sorry. Sorry, I have a trouble. Just a moment, please.
No, when you're talking about waves. Okay, please remember short wave.
Okay, start again.
Frequency, large energy. And when you look at this, there are all kinds of different light. The light that we normally talk about in our ordinary lives is is what we call the visual light. This is the light that we can see. And as you know, if you have a short wavelength, it starts from violet or blue and then goes through green, yellow, orange, red. Yeah. And red has a longer wavelength. Longer. So visual light, the light that we can see, has a wavelength of 400 nanometers to 700 nanometers. Okay. Now, this shows the wavelength here, wavelength lambda. So you can have light with very short wavelengths. This is micrometers to very long wavelengths. And if we go from the short wavelengths, you have gamma rays, X-rays, ultraviolet, visual, infrared, microwave, and radio waves. And as I said, short wavelengths means large energies, and long wavelengths means small energies. So you might know that gamma rays can be very, very, it has a big effect on your body, right? X-rays also, if you get too much X-rays, you can get cancer, you know that. And you may know that ultraviolet or UV light is not very good for your skin, right? So these short wavelengths or large energy waves can be very, it can have a big effect on humans or living things. If you go on to the long wavelengths, like infrared, you might know that infrared light or infrared rays is what you feel when you feel warmth, like from a stove. Yeah, far infrared, maybe, you know. Microwaves, you can use as a microwave oven. Radio waves, it's what you have with the radio. So these have much lower energies. Okay, so please know that there is a lot of kinds of wavelengths in light. And the light that I will be talking about today is mainly the visual and a little bit into infrared, a little bit into ultraviolet. So this is the light that we can see, or which is very close to us in our everyday life. Now, when we talk about light and materials or foods, there's lots of different interactions that light and materials have. So let's see what kind of interactions we can have. So when you have a light that is coming in to a material, something, first you have the reflected light, the light that comes back. This is the kind of image that you can get from reflected light. And some of the light is absorbed and the rest is reflected. Okay, so you get some absorbance and you get some reflectance. Some of the light is maybe transmitted. It goes through the material and then out of the other end. So this is the kind of light that is transmitted. You have the light from the back, it goes through liquids and then to your eyes. Okay, so this kind of light and this kind of light, you see that there's a difference to your eyes as well, right? There's a difference when you measure light like this. You need to be sure of what you are trying to measure, reflected or transmitted. There's also scattered light. Scattered is the light that goes a little bit into the material and it bumps into like cell walls maybe, and then comes out at the end. When light is scattered, it basically becomes kind of white. So here is an example of scattered light. This is egg whites. And you know that egg white, when you crack an egg, the egg white is transparent, right? It's not white, it's transparent. But if you mix it, it becomes white. And that's because there's a lot of air that is inside the egg white. And because of this air and egg white, there's a lot of walls or bubbles in there. Because of these lots of walls, the light gets scattered. It bumps into the wall, it goes the other way, bumps into the wall, goes another way. That's scattering. And because of this scattering, the egg white, which was transparent at the beginning, it becomes white and it's not transparent anymore. So this is a difference in scattering. It's not absorbance. There's no change in chemistry, but there's a change in physical part. There's also another type of interaction which is called fluorescence. Fluorescence is when the material first absorbs the light, but then gives out another kind of light. So this is a kind of mushroom which gives out fluorescence, and the background is black because the light that we are shining onto the mushroom is UV, so ultraviolet. We cannot see this kind of light, but the mushroom absorbs the ultraviolet and then gives out the green light. So this is another kind of interaction. So you can see that with light, there are all kinds of interactions that happen, and we are trying to measure this. Let's see the interaction a little bit more, and because this is very important when you are measuring food. When you have let's say we have an orange juice, okay? And this is a cup of orange juice where there's light that goes from the back. So there's light that is transmitted that goes through, as well as light that comes from your side and is reflected. When there's transmitted plus reflected, so transmittance plus reflectance, you get a kind of yellowish color, which we associate with orange juice, right? Now, if we put this orange juice in a chalet and you put white paper at the back, there's no transmitted light. There's no light that goes from the back to your eyes that goes through, right? So this is orange juice, which is seen only with reflectance. You see that the color is very different. It's kind of brownish, right? This is not really a color that we think is orange juice, but it's actually the same. This color is this. So you will see that the color will be different depending on what kind of interaction you use between the material and the light. So when you want to measure, you want to make sure that you are always measuring the same way. Are you always measuring with transmittance, or are you always measuring only with reflectance? Because if you're going to use either ways, the same orange juice, the color is going to be different. Okay, so please be careful for this. So this is the example that I was explaining with little or no scattering. It's only transmittance. You see that the egg white is kind of yellow or transparent, but if you mix it with air, there is no change in the chemical part, but if you have a lot of scattering, there's a lot of bubbles and cell walls, then you see that this becomes really white and not transparent anymore. Okay. This is fluorescence, where you have a UV light that you cannot see, but if you shine it onto a white shirt, you can see that this is blue. So blue light has a wavelength of around 450 nanometers. The light that we are shining onto the shirt is 350 nanometers. So this is fluorescence. Fluorescence is when you have a different light that comes out when you shine light on it. Okay, next I would like to explain the Lambert-Beer law, which is the basic law that explains the relationship between the concentration of normally a liquid or a sample and light intensity. This part is probably the most difficult part of today's lecture, so please try to stay up with me. Okay. So we're using light to measure something of our sample, and normally it would be some concentration of something that we are interested in. For example, sugar, right? We want to measure the concentration of something, and we use light to measure it. So the Lambert-Beer law, I will explain the law first, give the equation first, and then explain why it is like that. Okay, so the Lambert-Beer law says that if we have a light that is coming in, we will say I0, and the light that comes out, we will say IT for transmittance, right? The absorbance, we can define a thing called absorbance, which is proportional to the concentration C. And because we want to know the concentration, right? So if we can get an equation like this, we can calculate the concentration of this sample from A and this coefficient epsilon and the length of the light path, L. So we just have to divide A by epsilon and L. Well, we have to calculate epsilon, of course. And this absorbance can be calculated by taking the log of IT divided by I0. So I think first you will think, why do we have to take the log? And I would like to explain that. Okay, now let's see what this means. I would like to think of that we have a liquid, and let's say that this liquid absorbs light, so that in this small length dx, the intensity becomes half. Okay, let's say we have a liquid like that. So the incoming intensity I0, after dx, it becomes half I0. And then after the next dx, it becomes half again. So it becomes a fourth. And then after the next dx, it becomes half again. So that will be an eighth. So the light that transmitted through this, it will become an eighth of the original IO. IT equals 1/8 of I0. Okay. Let's say we have a liquid where the concentration is 2 times higher. Okay. What would the transmitted light be? Would it be half of this? Let's see. So if the concentration is 2 times more, the incoming light I0, it will become a fourth in the first dx. Then during the next dx, it will become a fourth again. So that's a 16th. And then during the next dx, it will become a fourth again, which is 1/64. Right? So if the concentration is 2 times more, in this case, the light intensity becomes an eighth. So it's not if the concentration is 2 times, the transmitted light would be half. it's actually an eighth. So this example, it's a simple example where we really divided the light path into small areas, right? Already you can see that it's not like a linear relationship. It's not like 2 half. If the concentration is 2 times, it's going to be an eighth. Okay. Now, so that will say that the concentration is not linearly related to the transmitted light, right? Now let's calculate how much light is absorbed during this dx. We'll say that this is di. So the amount of decreased intensity we will say as di. So how much light has decreased during this part? It's IO minus a half IO, which is half IO, right? The next part, from here to here, di will be a half IO minus a fourth IO. So it's going to be fourth IO, right? The next part, it's the same. It's the same. A fourth minus an eighth. So that will be an eighth of IO. So you can see that the decreased amount of intensity is getting smaller and smaller and smaller as the light goes through this liquid. Okay. So from these two things, we can get an equation that says that the amount of decreased intensity is proportional to the concentration. It's also proportional to the incoming intensity. So that is saying this. If the incoming intensity is high, the amount of decreased intensity is high. If the incoming intensity is low, the decreased intensity will also be low. Okay, so the decreased intensity is proportional. Proportional is hide to the concentration and the intensity, and also, of course, this length. We haven't changed this length, but if you can imagine that if the length is longer, it's going to be more, decreased more, right? So we can say these three things. And the reason why there's a minus is because it's decreasing. So we put a minus there. There's a way to calculate this type of equation, and maybe you already know this. The key is to put the same letters in the same place, right? So you move the I to this place, and K and C don't change. So you can just use them as constants. What you do is to integrate both with I and X. So what you get in the end, because 1 over X, if you integrate 1 over X, you get a log, right? So this becomes log, and then this just becomes L because it's a dx. It just becomes X, and then you put L and 0. So in the end, you get this minus log IT over I0 equals KCL. And this is what we said in the beginning. I just used a K because it's as a constant, but normally we use epsilon as the absorbance coefficient. And we define this as the absorbance. So when we calculate the absorbance, what we do is we measure the light that is coming out, the light that has come in, and we take the log of it. And that's the absorbance. From the absorbance, we can calculate the concentration of this liquid. One important thing that you can get from this, that you can know from this equation, is that when you measure absorbance, this value of absorbance shouldn't be very big. What I mean is, for example, if A is 2, let's say, this minus log 10 IT over I0 equals 2, right? This means that IT divided by I0 is 10 to the power of minus 2, or a hundredth. This means that IT, the transmitted light, is only a hundredth of the initial light. If A is 3, IT is only a thousandth of the initial light, which is very, very weak, right? So when you do this kind of measurement and you get a measurement value of, let's say, over 2, that means that the light coming out is very weak. Your sample is too concentrated, or the concentration is too high, and the light coming out is so weak that you can easily, the machine always has a little bit of noise to it, and because of the noise, the IT will be easily affected by this noise if the transmitted light is too weak. So there's a general rule that you should adjust the concentration so that, oops, this is a mistake, so that A is below 2. This is a mistake. A should be smaller than 2, which means that the intensity coming out is closer to I0. In that case, the noise will not affect I as much. So this is a very important thing when you are measuring with light.
Okay, this part is over. Next part will start 10:10 in Taiwan time, right? Thank you. Okay, let's start the next part.
Okay, in the second part of the lecture, I would like to explain how colors are expressed. One thing, so first I would like to explain how humans see color. Because, like I said in the beginning, a lot of the evaluation done on foods is done by humans. So when we want to use machines instead of the humans, we try to make the machines based on how humans see colors. So first, it's very important to know how we, with eyes, see color. So how humans see color. And one thing that is very important here, that all sensors, including the human eye, can only detect intensity. Intensity means dark or light. There's no color to it. But we see color with our eyes, right? And in order to see colors, that's a different thing from dark and light, we need to have multiple sensors. With only one sensor, we can only see dark and light, which is like grayscale. So light is white, dark is black, gray. And in order to see color, we need 3 sensors. And how we see color is we have 3 sensors, and the color is recognized by the ratio of the 3 sensors. More specifically, in the eye, there are 3 types of sensors. One is blue, or B. The second one is G, or green. Third one is R, or red. We have 3 sensors, B, G, R. And let's see if the first sensor detects high intensity and the 2 other sensors detect low intensity. We sense that the color that we're seeing is blue. If the second sensor, G, is high and the other 2 are low, we detect that the color is green. If the third sensor intensity is high and the other 2 are low, we detect the color red. And for example, if we want to see yellow, both G and R are high while B is low. So by the ratio of these 3 sensors, we can detect colors. And in the eye, we have these 3 types of sensors, which are called cones. And they are each sensitive to blue, green, or red. This is a cross-section image of the human retina, the place that we see in the eye. And there are different cones, like here. And this is where these are all sensors. And these, to repeat again, these can only detect if the light is light or dark, only light or dark. But by the combination of the 3 sensors, we can detect all the colors. So this is how humans see color, and this is the basis of how we make machines to detect color as well. So let's say we can see some tomatoes, and we see some green leaves in the background. So the red cone, the cone that detects red, or the sensor in our eye that detects red, it is seeing an image like the one on the top. The green cone is seeing an image like in the middle, and the blue cone is seeing an image like at the bottom. So these are only black and white, right? Grayscale images. You can see the red part, the tomato part. The red cone is seeing a very bright color, so very light color, and the other two cones are detecting a dark color. So by the combination of this dark blue, dark green, and light red, we see red color. Let's see if there's a green part, green leaves. The intensity will be high in the green cone, but low in the blue and low in the red. So let's say we take this part, take this color. If we see the intensity of the red and the green and the blue, it will be like this. On the other hand, if we take a green color, intensity will be high in the G, but lower in the red and blue. So by these combinations, we can see colors. And based on the way that humans see colors, we have a thing called the RGB color coordination system. This is like a copy of how humans see color. So it's the same thing. If we express the lightest color in 1 as 1 and the darkest color as 0, the red being 0, green being 0, blue being 1, that will be a blue. If we say that the red is 1, green 0, blue 0, it will be a red. There's no part where only G is 1, but by combining the intensity of R and the G and the B, we can express all these colors. Plus, if all R and G and B are 1, we get a white. If all R and G and B are 0, we get a black. So this explains how, for example, if we mix this green and the blue, which means the G is 1, B is 1, R is 0, we get this light blue color like as shown here. This is called the RGB color coordinate system. And this is the way, for example, like TV screens or computer screens show color. So there are very small dots of red and green and blue. And by combining the intensity of these 3 colors, we can express any color that we want. So that's the same. When I showed this tomato photograph on my computer screen, what is actually being processed inside the computer is that we have a red image, green image, and a blue image, and they're all just numbers. So intensity values. If the value is high, we get a white. If the value is low, we get a black. And we have 3 sets of data, 1 for the R, 1 for the G, 1 for the blue, 1 for the green, 1 for the blue. And by combining these 3 intensity data, we get the color image. So For example, if you take your camera and if you take a digital camera and you take a photo, what you're seeing is colors. But when you take that data out and you can process it with a computer, you will actually see 3 images. One in the red, one in the green, one in the blue, and intensity values for these 3 colors. It's very important to know this because, for example, if if you use a camera to do some evaluation, you will always have to process this 3 color intensity data. So this is the RGB color coordinate system. There are other kinds of ways to express colors, and another very important color coordinate system is called the L star, A star, B star color coordinate system. So in the RGB, we used the red image, the green image, and the blue image. L star, A star, B star is different. In this coordinate system, L star explains the lightness, so dark to light. A star explains the green or the red, and B star explains the blue to yellow. So this just shows the A star and the B star part, but the A star and the B star part explains the color. And then to add to this, we have the L star, which explains the lightness. As you can see, if you have A star minus, you get a green. A star plus, you get a red. B star minus, you get a blue. B star plus, you get a yellow. And then all the intermediate colors you can explain by A and B. What's good about this is this color coordinate system is close to how humans perceive color, which means that if values are very different in the L star, A star, B star color coordinate system, humans also feel that the color is very different. This is different from the RGB because in the RGB color coordinate system, even if the values are very different, that's not always how humans feel. There are some colors which humans can see very clearly that it's a different color, while for some other colors, humans cannot see the difference. The L star, A star, B star is very close to how humans feel about colors, if one color is similar to another color or not. So this L star, A star, B star color coordinate system is used a lot to evaluate the color of food or industrial products. For example, this is a plot of how of the color of bread during baking. So as you can see in the beginning, the color is light, while as the bread is being baked, it becomes dark. And so these colors are all plotted in the A star, B star, L star matrix. And if we take one bread and bake it in the oven, the colors will follow this kind of line. So this is showing how the color looks from the top. And then if we look at the L, it will be going down. So if the value L star is high, it's very light. If the value of L is very low, it will be dark. So by looking at this matrix from the top, if we just look at the A star and B star, it will be the color of the bread will be forming like a kind of round shape. If we look at it from the side, we will be seeing that the L star value goes down as the bread is being baked. So this is one kind of way how we can use the L star, A star, B star color coordinate system to evaluate food. Okay, next I would like to go on to the fourth part of this lecture and talk about how light is being used to monitor food. So examples of how to do food monitoring by light. First, I would like to talk about how visual light, so the light that we humans can see, is being used for food monitoring. So I talked about this before, but light has many kinds of wavelengths from 10 to the minus 6 micrometers, gamma rays, to long radio waves. And the part that we humans can see is the part, well, in the middle, which is around 0.4 micrometers to 0.7 micrometers, which is around 400 to 700 nanometers. And the light with the shortest wavelength that we can see is violet, 400 nanometers. The longer wavelength is red, or 700 nanometers. This is the part that we can see. And because humans can see this part of the light, a lot of light sources, which means the light that we shine, or sensors like cameras, there's a lot of these light sources and sensors. They're cheap and high quality because we make things that we can see, right? So I said in the beginning that there's two types of monitoring, one point measurement and multiple point measurement. So because the light sources and sensors are very cheap, a lot of the monitoring done in the visual light part is multiple point measurement, or images, or line sensors. So these get a lot of data at once. So let's see what kind of monitoring is being done with visual light. Okay, this is one video where visual light is being used to sort dates. Dates are like plums, you know? Okay, so as we saw, we'll go through this again. You see that here there are light sources or lights at the top, and as the dates go through this system, there are cameras which take images of the dates. Yep. Okay. So this is where the cameras are. There's a strong light that comes from the top, and it's very quick. So there are cameras here, and the images come to this computer, and by assessing the images, the machine will automatically find out if there's loose skin, so if it's not fit onto the fruit very well, or so this is analyzing the shape and the color. It's also, if you can see after this, it's gonna analyze the shape, so the width and the height. So depending on the size, it's going, the machine will sort out these date fruits into high quality or low quality. So this is done with a camera. And as I said in the beginning of this lecture, cameras are multiple point monitoring. So there's lots of sensors, and by taking the whole image, this camera assesses the quality of these dates. So this is one example how light in the visual wavelength is used in food monitoring. Now let's look at the wavelength which is a little bit longer than the visual wavelength area. This is called infrared because it's a little bit longer than the red color. Infrared light can measure vibrational energy of molecules. You might know that molecules vibrate like this, and infrared light can measure this vibrational energy. And by measuring this vibrational energy, you can find out, for example, if the molecule has an OH or CH or NH inside the molecule. And you can find out all the chemical molecules that are connected to this. And in the infrared area is very wide, so from around 700 nanometers to, you can see, 1000 micrometers. It's very long. And the part which is very close to the visual area, we call it the near infrared. So this is only part of the infrared. You can see that it only goes up to around 2500 nanometers. Well, around here. It's only part of the infrared. We call near infrared or NIR. And this is used a lot in food monitoring. One very important thing about this NIR light is that it has only weak absorption. It only absorbs it. The light is only a little part of the light is absorbed, not all of it. Is this good or bad? Well, it's not so good in the sense that if you have a little bit of the chemical that you're interested in, the NIR light is absorbed only a little, so it's it's very hard to sense, to measure it. But weak absorption also means that the light isn't absorbed very much, so it travels far inside the sample. So because it goes inside the sample, it can be used to measure what is inside that, for example, fruit or vegetables. If light is absorbed a lot, it will not go inside, but it will just be absorbed in the, for example, the skin or the very surface of your food. Actually, when we try to measure food, we want to see what is inside, right? For example, how much sugar content is there inside the fruit? We know about the outside because we can see it. We want to know what is inside. The NIR, near infrared light, is very good for measuring because it's not absorbed very much. So it goes far inside the sample and it goes through the sample onto the outside. And by measuring how much light is absorbed as the light goes through the sample, we can measure how much of that constituent is inside that sample. So this is the very, very important thing about NIR, is that because it has weak absorption means that the light travels inside the sample, and so it's possible to measure the constituents inside. If you think about the light that we see, or visual light, it gets absorbed at the surface. That's why you can't see through things. If you can see through things, it means that the light is going through and then out into yourself again, right? Everything that is opaque or not transparent to us, it means that the light has been absorbed at the surface and it's not showing anything inside. NIR light we cannot see with our eyes, so we cannot imagine how a sample would look in NIR light, but the important thing is that it goes inside the sample and then out again. The not so nice thing about NIR light is that the spectrum is very complicated. We will look at this later. I will show you some spectrums of NIR, but the spectra is very complicated, so we cannot just look at it and say, okay, there's so much sugar in this sample, or there's so much acid in this sample. The spectrum contains that kind of information, but we cannot just look at the absorption and determine that. We need to do a lot of multivariate analysis and use a kind of method called chemometric method to obtain this kind of information that we need. For example, if the apple is sweet or not. So this is a kind of drawback of near infrared light. Another drawback is that we can only measure organic components. For example, if we want to know the salt content, salt is an inorganic component, right? We cannot use NIR to measure inorganic component directly because there's no absorption of inorganic components with NIR light. But we can measure, for example, salt content indirectly because If you think about salt, when there's salt mixed with water, it will change how water absorbs NIR light. So by measuring the spectrum of water, and we can indirectly predict how much salt there is in there. So that's not directly looking at the salt, but by measuring the spectrum of water, we can indirectly get information of how much salt there is. So that's another drawback of inorganic of NIR light. But because of this one very important point, that the absorption of NIR light is weak, it's used a lot to measure the quality of foods. Okay, let's see one example of a spectra of NIR. This is an absorbance spectrum of cookie. So you know that cookie has flour in it. It has fat in it, like butter or oil. It also has some water from maybe if you add an egg in it, or there's a bit of water in butter as well. So if you look at the spectrum of a cookie dough, you will see that there's absorbance of water here. There is also absorbance of fat here. And maybe there's a little bit of absorbance from the CH in the flour, or sugar maybe. This is basically what you will see. And from only this spectrum, we cannot calculate how much fat there is in there or how much water there is in there. Okay, this is the absorbance that we talked about before, how much light has been absorbed by this cookie dough as we shine light on it. So this is also similar to the one that I showed. This is an absorbance spectrum of wheat. And from this spectrum, if we take the value at 1680, 2100, 2180, and we add it up like this, we know that it will give us very high correlation to the protein amount measured by standard methods like the Kaldal method. So this graph shows that the y-axis is the value or the amount of protein calculated from this equation, and the x-axis shows the value measured by the Kaldal method. And you can see that there's a very high correlation between these two methods. So this means that once this kind of standard curve is made, you don't have to use the Kaldal method anymore to measure the protein in wheat. You just have to measure with NIR, which is very easy. You just set the you just set the wheat on the machine and you just press the button, the machine will measure the absorbance. You will get the value in a second, 1 second. Well, if you have done the Kaldal method, it's very hard, right? I've done it before, but you have to add acid and then you heat it up. You do this, you do that. It takes 1 day. So once you have this standard curve, which shows the correlation between the Kaldal method or standard method, chemical methods, and value calculated from the spectrum, it will be very easy to measure, for example, the protein in wheat. But you need to do a lot of experiment in order to get this equation. It's a similar thing with fruits. This is an example where we're trying to measure the sugar content of an orange. And that's also very important. It's very important that the light goes through the skin of the orange, which is very thick, and through the orange and out, because otherwise we can't measure what is inside. And in this image, you will see that the lamp is on the side. The light will go from the lamp into the orange, and the spectrometer or the sensor is in here. It will measure the light that has gone through the orange and out of the skin again. And so the light that is measured here, it will have the information of what is inside the orange. And this graph shows the value measured with the light sensor, as in here, versus the sugar value measured by refractive index, the Brix percent, which is the standard method. But to measure this, you have to squeeze out the juice from the orange. And if you do that, you can't eat the orange anymore. So once we get this correlation between the light sensor value and the refractive index, we only have to use the light sensor, and we know how much sugar there is in here. The very good thing about this method is that it's fast, plus the orange is not going to be destroyed or destructive. So you can still eat the orange after it's been measured. See if we can see this video.
久保田が開発したフルーツセレクター搭載型選果機。選果工房は糖度、酸度、重量を同時に測定することができます。
大型の選果場で使われる糖度計っていうのは1台が1000万円以上とか、非常に高額なものでして、こちらは糖度計の方は1台100万円ぐらいということで、担い手農家さんというか中規模農家さんにもお使いいただけるような価格に設定しております。こちらは光センサーを用いまして、トマトの中を光を通しまして、その返ってきた光を分析しまして、糖度を測定しております。
フルーツセレクターを2台搭載したユニットにおいて、1人でトマトを測定した場合、1時間に約2000個を処理することができます。
この配下するとこを増設したり、このフルーツセレクター計測部の台数を変えたり、タッチパネルをパソコンに変えたりという、そういう拡張性はあります。今は糖度と酸度を測っているだけなんですが、今後は腐った果実を測ったりですね、他の障害度を測ったりとか、そういうふうにして選別できるような展開を考えていきたいなと思っております。
糖度と酸度を測る品目としては、トマトとリンゴ。糖度を測る品目としては、梨、柿、キウイ、ビワなどがあります。パソコン仕様の標準タイプは、フルーツセレクター1台、配下工数7つで構成され、販売価格は約510万円です。
Okay, so this video shows a fruit selector. It's called a fruit selector, which is made by a machine company in Japan. And what it's doing here is that it's measuring the sugar content and the acidity, the acid content of tomatoes. Oops. So you can see that there's a light that comes from beneath. Oops. you can see that there's a light, yeah, that is shining from beneath, right? And then in this machine, I think the sensor is beneath as well, underneath the tomato as well. The light is shining. I think it's from the side here, and then there's a sensor beneath the tomato, and it's measuring the sugar content and the acid content. Nowadays, there's a lot of these small machines. It's quite small and not so expensive as the ones that were sold like 10 years or 20 years ago. So this is, for one machine, it's around 1 million yen. So yeah, it's expensive, but it's not as expensive. So, for example, a farmer can maybe buy one to sort out his or her tomatoes. So it's small, and as you can see, it's very fast. You can, in a few seconds, it can measure the sugar and acidity and the weight of this tomato. See, as you can see, there's light going out, and here it's measuring the sugar and the acidity and the weight.
大型の1000回100万円ぐらいということで、担い手農家さんというか、中古農家さんにもお使いいただけるような価格に設定しております。
So this is how NIR light is being used to monitor fruits and vegetables. Now here they're measuring tomatoes, but you can also measure other fruits like apples or pears, they were saying. Maybe for these for fruits like pears or apples, you don't really need to measure the acidity. They're also talking that they want to make machines that will detect some like spoiledness inside the fruit, if the fruit is spoiled or it's bad inside, but you cannot see it from the inside. They also want to use NIR light to detect that. Okay, finally, I would like to talk about how fluorescence can also be used to monitor food. Fluorescence can be seen in many kind of wavelengths, but here I would like to talk about fluorescence in the UV, ultraviolet, to the visual wavelengths. So if we go back a bit, visual light is from 400 to 700 nanometers, and ultraviolet is a little bit shorter than that. So, for example, from 200 nanometers to 400 nanometers. That will be the ultraviolet. Fluorescence has a very strong point that it's very highly sensitive to some constituents like proteins or color pigments. It can be like 1,000 times more sensitive than absorbance. So fluorescence is different from just absorbing. It will first absorb, then emit, give out light. That is fluorescence. Then it's very highly sensitive, but only some chemical components show fluorescence. Proteins and color pigments have fluorescence, but for example, simple carbohydrates like sugar, they don't have fluorescence. Simple fatty acids, they don't have fluorescence. So chemical components that don't have fluorescence, of course, they cannot be measured. So fluorescence is limited to the type of chemical components that can be measured. This is an example of the fluorescence of brown rice. And as you can see at the beginning of the storage, it's not so dark, it's not so light, it's kind of dark, but as you store it, the fluorescence becomes stronger. This is because maybe you cannot see it in the screen, but the fluorescence becomes stronger as the brown rice is stored. This is because when the fat is oxidized, it will emit stronger fluorescence. So this means that as the brown rice, there's some fat on the surface of the brown rice, the amount of fat oxidation, which tastes not so good, which tastes bad, it will begin to get lighter. So by using this fluorescence, you can detect how much the fat has been oxidized. Okay, so this is an example of how fluorescence can be used to monitor food.
Okay, this part is over. Next for lunchtime, after the lunchtime. Thank you.